Okay, so today, last time we stated this lemma without proof. So we will prove it now. So it will be the same kind of proof. We will make some pictures, and it will be, as yesterday, straightforward. Okay, so A x star. This is the dual of the morphism AX. So you write AX and dual morphism. Then consider this box. Oh, this one is too. It's not visible. This one. Okay. Consider this box in which we will apply the previous lemma. So remember this lemma. So we will apply this equality on the green box here. So we get, so by lemma, the previous lemma 2.5, we get that we can move the morphism on the right. So A inverse x star, like that. And then the remaining part. So let me draw the box, the green box. That's okay. And then we just need to apply again the zigzag relation. To get only this, which is okay. So let me write a bit of some object. X star, X star, X star. Okay. So you get the first equality. So the pivotal morphism AX, if you consider its dual, is the same as considering the pivotal for X star inverse. Okay. So now what about the second equality? So for the second equality, remember that we already observed that if F is an isomorphism, then F star inverse equal F inverse star. But in fact, so about the second equality, consider, so we have A X inverse star. Okay, so you can apply this observation we proved yesterday. So it is equal to A X star inverse. And that is equal to, now we can apply the first equality. So that's equal to A inverse X star inverse first equality. So it is, you apply inverse 2 times, so it is AX inverse, AX star. Okay, so we have the second equality, and then you just need to apply this one and this one to get this one. Let me write it finally. AX double dual. This is equal to AX dual. So by the first equality, it is A inverse X star, which by now you apply the second equality with X star. So you apply this equality, but with X star. So now you get X double star. So it's equal to AX double star, second equality with X star. Okay, so we are done with this lemma. Now we can introduce, we will introduce a very important notion called the trace. So it's very important. Okay, so so let C be a pivotal monoidal category. Monoidal category. Let A be the pivotal structure. Let X be an object in a category. In the category. Now we consider a morphism. Let alpha be a morphism between X and itself. And we will consider the trace of alpha. The trace of alpha according to the pivotal structure. A is defined as follows. Trace. So this picture, so trace of alpha defined as, so you consider, you draw alpha, X and X, you put a pivotal structure. So now you are in X double star. You put evaluation coevaluation map identity. Here you have X star. So this is what we call the trace of alpha. So remember that this should be interpreted as a morphism between one and itself. So in a fusion category, the unit object is simple. So by Schur lemma, the morphism between the space of morphism between one and itself is one-dimensional. So it's equal to the field. And so in the fusion category, more generally, when the unit object is simple, the home space are vector space, the trace is a scalar. But in general, it's not a scalar. Okay, and then we can use this trace to define a notion of dimension. Dimension. So the dimension will be, the dimension of an object will be the trace of the identity of this object. So following definition 2.7. When I draw following definition, I mean you just you have exactly the same constraint. This is the same case as this definition. You can define the dimension according to the pivotal structure A to be of the object X to be the trace of the identity, as I said. Okay. So it's a bit boring to have to write the index A every time. So when there is no confusion, you will avoid this index A. If no confusion is possible, we will write trace and dim without A. Okay. So we can prove the first lemma involving trace and dimension. So following definition 2.7, assume, which already followed 2.8. So you have X, we assume X to be simple. Assume that X is simple. So it's a simple object. And assume that the dimension of X is non-zero. Then we will prove that, in fact, alpha, so the alpha here, the alpha here, any alpha, so this space is one-dimensional, and any alpha is of this form. Dimension X inverse trace of alpha identity of X. So any alpha is the multiplicative, is identity up to a multiplicative constant. And in fact, this constant is precisely this. So, proof. So, as usual, you apply the Schur lemma. By Schur lemma, the home space between X and itself is just K identity, is one-dimensional. So So let me check. Maybe we need to be k-linear because we need the home set to be a space, to be wait. So we may need k-linear assumption to this to be a space, k vector space. Anyway, it's, I guess maybe we don't need. Maybe we don't need. Anyway. I'm not sure. We can assume it is k-linear. In fact, all what we are doing will be applied for fusion category, which are already k-linear. Let me write some. Okay. So alpha can be written as identity times a constant. So there is k in the field such that alpha equal k identity of x, then trace of alpha is trace of k identity of x is k trace of identity of x is k dimension of x by definition. So k equal trace of alpha divided by the dimension of x. That's why we need dimension of x to be non-zero. And this is exactly what we wanted to prove. We get that alpha is k times identity with k like that. So that's okay. Okay. Next. So now we will so we have trace of alpha. So you can write the same definition for trace of, you can write the same picture for trace of alpha star, but we will need an alternative way for trace of alpha star. So let me prove the following. So following definition 2.7, the definition of the trace. The following equality hold. The trace of alpha star. So according to the definition of the trace of alpha star, you just put alpha star here, star here, star here. And here it should be triple star and double star, etc. But what we will need is the following, which will be proved with some straightforward argument again. X star. Okay. So proof. So the usual way to draw the trace of alpha star, as I said, is by definition. So we draw alpha star, X star, X star, et X star, X triple star, like that. But here you can replace alpha star by the definition of the dual of a morphism. So it is alpha dual like that. And then you write what remains. Okay. Next, we apply the lemma 2.5, so the lemma with which we can move this on the other side up to some modification. So let me write like that. You apply the lemma 2.5. And we get the other way. So alpha you have that. Now it's on the other side with this modification. And then by zigzag, finally, by zigzag relation. So you apply zigzag relation here. So you have one zigzag relation here. So you get X alpha like that. Okay. And this is what we wanted to do. So we are done. Okay. So what's the point of considering trace of alpha star? The point of that is for the next definition of sphericality. In fact, the definition of sphericality involves trace of alpha and trace of alpha star. Okay. Definition. Spherical. Okay. So a pivotal. A pivotal monoidal category. Pivotal monoidal category C is called spherical. The pivotal monoidal category C is called spherical if for any object X and for any morphism alpha between X and itself, the trace of alpha equals the trace of alpha star. So if for any object X in C, and for any morphism alpha in home C between X and itself, then trace of alpha equals the trace of alpha star. And we will see in some coming proposition the next lemma, we will see why this is called spherical. Why it is called spherical? Because it's like if you are doing pictorial calculus on a sphere. And when you are on a sphere, you can go, I will explain. So before that, before stating and proving this lemma, let me put a remark. In fact, the definition of spherical can be simplified. So there is an alternative definition which is simpler. So in particular, so I will, if it is spherical, this will imply something, and in fact, so this something is simpler, and in fact the converse will be true, so that remark will provide a simpler alternative way to define spherical. So in particular, spherical imply that for any object X, then dimension of X equal dimension of X star. If in the definition of spherical you only consider the identity morphism, you get that. Because trace of identity of X equal trace of identity of X star equal the trace of identity of X star, like that. But as I said, the converse is true. So to define spherical, you only need to consider dimension of object. And in fact, what is also even true is you only need to consider the dimension of simple object. If the dimension of simple object X equal to the dimension of X star for all simple object X, then it is spherical. The converse is true on the tensor, but we need to be on the tensor category. At least it is proved in EGNO book for tensor category. Let me write this reference 4750. So as I said, even assuming X simple. Okay. Okay, so let me state a lemma about spherical monoidal category, and I will explain why it can be seen as a graphical calculus on a sphere. So lemma 213. So I am following the notation, the numbering in my paper. So let's see be a spherical monoidal category. Spherical monoidal category with pivotal structure A the pivotal structure. Et we consider two objects, X and Y, and you will consider a morphism alpha between the unit object and Y star X tensor X star. So let X, Y be object in the category C. Let alpha be a morphism in from C between 1 and Y star tensor X star. And we will also consider a morphism beta between 1 and X tensor Y. In C 1 X tensor Y. Then to consider the so alpha, you have the following equality: alpha beta. So Y star X star X Y. Consider this evaluation map. This is equal to so alpha beta you add the square of, so I have to be careful about that. Wait, there may be a confusion here. So the square of the pivotal structure for X star. Here you have that. Continue here. So and so you go the other way around. And here it's okay. So you see what happened. So so let me simplify the notation, but let me write so I will write after. Okay, so it's okay. A equal A. So let me for now let me write, and I can put smaller box. It will be more beautiful. So A2 square. Okay. So wow. Okay, so what about spherical structure? So consider this. So this equality is true in the spherical case, but it's not true in general. So what I want to say. In fact, it will be more convenient to explain the spherical structure with the next equality. So I will write that in more details. But this is also equal to so alpha beta like that. And like this. So what about the spherical structure? White X. So consider this. So this is not different equal to this in general, but in the spherical case, assume that this pictorial, this graphical calculus, this picture is on the sphere. On a sphere. Then this string can be moved. So you have the sphere, you have this string, and you can move this string on the other way of the sphere, such that it can be here like that. So this is what we did. We have that. We can move. So we don't apply this sphere intuition. In fact, this will be proved. But you can see intuitively that it is like in the sphere, you can move this the other way. Like when you move it on the sphere, the other side of the sphere. That's one reason why this is called spherical. Okay. So let me prove this equality. So proof. I will prove the first equality. The second will be the same. ID by zigzag relation. So we will need to apply zigzag relation and something composed of inverse equals identities. So zigzag relation and AX composed of AX inverse equal identity of X. So we will apply that. So you start from alpha, beta, like that. Y star, X star, X. Now, we can, in fact, we can deform a bit this string by zigzag relation. We can do something like that, if you like. There is no sphericality here. To do just that, you just come back. You don't go the other way yet, not yet. So this is, yeah. So you have one spherical structure, one zigzag, another zigzag. You can do that. And we will add this identity here. We will add these two things. So let me draw that. So alpha, beta. So the zigzag. And the identity as a composition of one morphism and its inverse. Then like that. And here, no modification. So I hope it is clear that this is just application of zigzag and this trivial identity. Okay, now we will here, it may be, I want to say that the next argument will be the less straightforward up to now. So it is still straightforward, but you have to be careful because the pictures start to be big. So we will need to consider a morphism. So here you have X, here you have X. We we will consider the morphism between X and itself, like that. So let me check, not this one, not like that. Like that here. So this. So what is inside that can be seen as a morphism between X and itself. And then you have this extra string, which is this one. You have this extra thing, which is a definition of a trace. So you get that this is equal to the trace of some gamma, with gamma be a morphism between X and itself, as I explained just before, as follows. I will redraw just gamma. So you have gamma equal alpha, so you have beta, you have this X, and so this like that. A X inverse, you have this X, and this is going like that. Okay. So this is a well-defined morphism between X and itself. You start from X, the input is X and output is X here. Okay. And what remains to get the full picture is this extra thing. But this is exactly taking the trace of gamma by definition of the trace. Remember, definition of a trace, which is here. You are adding something like that. So this is precisely the trace. Okay. Okay. So the proof is not finished, but I will finish it after the pause because it is the pause time. So pause. We'll finish after the pause. Oui, vas-y, Harold. Okay, so let me finish this proof. So we apply zigzag relation here plus some triviality. And the trick here is to consider the morphism gamma between X and itself. So this morphism gamma. And see that this is a trace of gamma. Okay. So everything up to now, we don't need sphericality, but now trace of gamma by sphericality is a trace of gamma star. And we prove the lemma about trace of gamma star. So we can put the string on the left instead on the right. So by sphericality, trace of gamma equal trace of gamma star, and by lemma 210 proved today. So where is it? Here. trace of gamma star can be written like that. So trace of gamma star equal Ax inverse gamma, so x. Okay. No, now you put the picture of gamma here, you get so the picture of gamma is like that. Alpha, beta, A inverse x, like that. Okay, so here we add the remaining part. So we add that. So A inverse x. Okay. Now okay. We draw it in red because I started to draw it in red. X. Okay. Now you can apply our usual lemma 2.5 to move. So we will. So this one you can put it here. It's okay, but you can move it here by applying lemma 2.5 up to some modification. You can do that here also. And then this will be moved here and again here. So you can group all this pivotal structure can be put together here. And this will exactly provide the. So I realize that I forgot to write something. So we will exactly get this one by moving everything here. Let me write something I forgot about. The definition of A2 x star. So here, where A2 is the natural isomorphism between identity of the category and the force dual functor, the natural isomorphism, which is the square of the pivotal structure A. Square of the pivotal structure A. Which is the square of the pivotal structure A. In particular, A2 x star equal A x triple star compose AX star. Or if you like, something more A square Z equal A Z double star A Z. So if you take Z equal X star, you get AX triple star composed with AX star. Okay, so this morphism should not be considered as the square of the morphism is AZ. Because the morphism AZ cannot be squared. AZ is between Z and Z star, Z double star. So we cannot compose, they are not the same input, output are not the same. So it is square of the natural isomorphism A. And here this notation means that, so you have to be careful. This is exactly what we mean by that. Okay, so as I said, we finished with this picture. So by the lemma 2.5, we can move that here, and then what we get here is a composition. It can be moved here, etc. We can anyway, you can move everything here. And what you get here at the end is something like that. So which is because here you get AX square, AX star. You move here, you have AX star, and then AX double star inverse, and AX triple star. So you really have this with Z equal X star. Okay. So, as I said, the result follow by applying lemma 2.5 several times. How many times? One, 2. So let me start by this one. 1, oh, wait. So 1 for this one. 2, 3, 4. So we need to apply it 4 times. So result follow by applying lemma 2.5 4 times. And so the other equality, this equality, follow exactly by the same argument. Can be obtained by a similar argument. Okay. So now we understand now a bit of why this is called spherical. So now let me define the notion of Frobenius indicator. As I said, in this course, we will prove one conjecture involving Frobenius indicator. So this is not the main result of the course, but it is one result. Okay. So the Frobenius indicator. So we need to be on a K-linear pivotal monoidal category. Let's see, be a K-linear pivotal monoidal category. So again, the pivotal structure is denoted by A. We consider an object X in the category. Be an object in C. Now, we will consider the K-linear map from a home space to itself. So let E X N with this notation be the K-linear map from the space, this space to itself. With n greater than or equal to 1. And this map is defined as follows. This linear map defined as follows. Ex n of alpha, so alpha in the home space, defined as follows. So alpha. So it's a morphism between 1 and x tensor x tensor x. It's not x tensor n, it's x power tensor n. So you have x n times. So you do like that. A inverse x. So you see, you start from alpha. You do this modification, and what remain is still a morphism between 1 and x tensor power n. And this is a linear map. Okay? So the nth Frobenius show indicator of the object X will be the matrix trace of this map. The nth Frobenius show indicator of X is denoted like that. Nu nx, the matrix trace of this linear map. Where this is the capital T. Capital T is the usual matrix trace. Usual matrix trace. Okay. Okay. So, a small remark. If this home space, is one-dimensional, then the trace, the matrix, then this matrix is just a scalar, and so the trace is just itself. Right? So in the one-dimensional case, the trace is directly nu n of x. So if from C1x tensor power n is one-dimensional, then en x of alpha equal x alpha. Yeah. Wait. En, yeah, En. Yeah. Okay. Okay. So now we will prove that the formulation indicator power n is equal to what? So it's nth root of unity. Proposition 215. So let me see. Maybe I don't need to rewrite everything. So following definition 214. So we don't need to rewrite every assumption of this definition. If if this space is one-dimensional, then the Frobisher indicator is the nth root of unity. Okay, so proof. So the idea is to evaluate something in two different ways. Is to evaluate A defined as AXN composed n time of alpha in two different ways. So first way. Okay, wait. So I added an assumption. Alpha. So what is alpha? Yeah. With alpha, a non-zero morphism in space, this space. Okay. So the first way, on one hand, wait, 1 second. Okay. So what is A pictorially? A, you apply the map E and X n time. So you start from alpha. You apply it one time. Two times, three times, etc. Up to n times. X. So this is exactly the picture for A. Now, by definition of a dual morphism, so you have the morphism alpha, the dual morphism, double dual morphism. So you have, this is nothing but alpha double dual, and you have this. X inverse, X inverse. Okay. Now you apply the pivotal structure by monoid. The pivotal structure is monoidal, so you can group them together. Alpha double star A X tensor power N. Okay, but finally you again apply the pivotal structure. Remember that using the pivotal structure, you can write a morphism F as a using the double dual F double dual with the pivotal structure. We prove not prove. This is in the definition of the pivotal structure. So in fact, if you remember the definition of the pivotal structure, this is here you have one, but you can forget about that. This is exactly alpha. Okay. So we get that A is alpha. On the other hand, so A is, so A and X compose n time applied to alpha. So in particular, it's A and X composed n minus 1 time of A and X of alpha, which is, as we proved before, A and X composed n minus 1 time of eta and alpha. So where did we do that? Here. So where is it? Here. Yeah. Because this is one-dimensional by the assumption of the proposition. So it's okay. You can, this is linear, so you can put mu nx outside. This is equal to mu nx a nx compose n minus 1 time of alpha. And you can continue and finally get en x power n alpha. The conclusion, by these two different ways, we get that alpha is mu nx power n alpha. So A equal alpha, A equal mu nx power n alpha. But alpha is non-zero. So mu nx power n equal 1 because alpha is non-zero. Okay. So the Frobenius indicator is a root of unity. More precisely, the nth Frobenius indicator is the nth root of unity. Okay. Now, So we will prove something using this proposition. Okay. So we'll use this proposition to prove the following lemma. So you consider again so following definition, proposition 215. Following proposition 215, so the same assumption as proposition 215. So C is a k-linear pivotal monoidal category, A is a pivotal structure, X an object in C such that the Helm space between X wait. So following definition with n equal to. We need n equal to. So X is an object such that the Helm space between X tensor X and 1 is one-dimensional. Here we have Here it's between 1 and X, so I need to rewrite everything. Okay. I need to write because it's not exactly the same assumption. So let C be a k-linear pivotal monoidal category. Let A be the pivotal structure. Let X be an object in C such that Helm space between X tensor X and 1 is one-dimensional. So in the previous statement, it was between 1 and X tensor power. Here it's X tensor X to 1. So it's slightly different. Then, for any morphism, kappa in the Helm space between of morphism between X and X star, the following equality hold. So let me draw a picture and then with a formula. So AX, so the pivotal structure AX, X double star, kappa between X and X star. This evaluation map equal to the second from initial indicator of X star of this picture, kappa along X star, X. Okay, which can be written as this formula: evaluation of X star composed with pivotal structure X tensor kappa equal second from initial indicator of X star, evaluation of X composed with kappa tensor identity of X. Okay. So it will be a bit convenient to use this formula during the proof, at some point during the proof. So that's why I write it. Otherwise, I will not. Okay, proof. So, let me introduce, to simplify a bit, some notation to avoid to write X star everywhere. And kappa star everywhere. Consider Y to be X star and iota to be kappa star in C X star Y. Sorry, in Y star Y. So you have kappa is between X and X star. So kappa star is between X double star and X star, which is Y star Y. Okay. So yeah, so this notation is just to simplify the proof, to avoid a lot of star in the proof, too much star in the proof, but it's not really necessary. But anyway, consider the morphism alpha, identity of Y tensor iota, composed with the evaluation, the co-evaluation map of Y in, so this is in the Hom space of morphism between 1 and Y tensor Y. So this is nothing but this picture. Y star Y. Okay. So now, we will evaluate the E2Y alpha in two different ways. Let us evaluate E2Y alpha by two ways. So on one hand, E2Y alpha equal mu 2Y alpha because C1 Y tensor Y is one-dimensional, as this is a previous remark, one previous remark we said before. And so let me check whether we really need to redo that, because we already made an argument. It's not the same. It's not really the same argument. Okay, so we need to repeat this double way argument. On the other hand, so E2Y alpha is by definition. So let me, you can draw alpha, iota. And then you apply alpha, you apply E2Y. So you are doing that. Y, Y, Y star. Now you have a zigzag relation here. So So zigzag relation. So this is just that. Okay, y. Like that. Which is equal to, you can write it by as a formula, y inverse composed with co-evaluation map of y star. Here, y star, y double star. Okay, so we obtained this equal to this, and alpha is this. Now, if you replace y by x star and iota by kappa star everywhere, you get drawing formula. We obtain that kappa star composed with a x star inverse, no, not composed, tensor, composed with co-evaluation map of x double star equal nu x star identity of x star tensor kappa star composed with the co-evaluation of x star. So there is nothing here. I just the equality of the one way and the other way, and replace y by x star and iota by kappa star. Okay. Now you apply the right dual everywhere to the last equality. Plus some previous lemmas about how to apply the dual to a composition, how to apply the dual to a co-evaluation map, etc., etc. But with the right dual, which is exactly the same, plus some previous lemma restated for right dual. So exactly the same thing. You get, so you apply the right dual. So this will be changeable. You will get, so this will permute. This and this will permute. But this and this will also permute. Again, here, this will go there. And this, etc. So you get, but what we will keep, in fact, so the star, by applying the right dual, every star will be, many star will be removed, except this one. You will keep, but this is a constant. So this does not, applying the right dual will not affect this star. So the right dual of that will be evaluation of x star, then ax tensor kappa equal nu to x star evaluation of x composed with kappa tensor identity of x. Which is exactly this formula corresponding to this picture. So we proved what we wanted. OK. So it remains 3 minutes. So let me just state the next proposition involving again the second Frobenius indicator. Proposition 217. Okay. So let's see, be a pivotal structure. Pivotal fusion, fusion here. We need fusion category. Let A be the pivotal structure. Let X be a simple object. Be a simple object. So there are two variations here. The category is fusion and the object is simple, such that X is self-dual. Then the pivotal structure of X is given by the second Frobenius indicator. It's just the identity times the second Frobenius indicator. In particular, if you apply it 2 times, A square X equals the identity of X, where A square is as before, A square from identity functor to the force dual functor is the natural isomorphism square of the pivotal structure. Okay. So this is one utility of the Frobenius indicator. In fact, using the Frobenius indicator, you can replace the pivotal structure morphism here just by the identity times the constant. And the constant is given by the second Frobenius indicator. So identity time a constant, this is okay because X is simple, but this constant is precisely given by the second Frobenius indicator. So that's useful. That will be useful for the rest of the course. So we will prove that next week. So we have finished. End of session. See you next week. Okay.